Hello and welcome to Trigonometry Lesson 3. This one is going to be titled More Sign Language. Before we get into the actual lesson, we want to do a little review of what we've been talking about lately and what we covered in our last lesson, which was number 2. So we have a Ferris wheel drawn again. We remember that it was the middle of our Ferris wheel was 30 feet off the ground, and our radius was 25 feet in each direction for our circle. We came up with an equation to tell us the height, and remember that we had a different equation for each kind of quadrant of our Ferris wheel. Sometimes we did 30 minus 25 sine of a number, and then we had some more stuff going on inside, whether it be 180 degrees minus 18t, or we had 180 degrees plus 18t, or 360 minus 18t, different combinations of that sort of thing. And so we're going to look at some more examples of that. Quick note on that, when you see this symbol right here, that is the Greek letter theta. Now, theta is a Greek letter that is used to represent an angle that is going to be your variable, an input, or an angle that you don't know. You don't want to use x for everything because x is usually representing a number or a value. Theta is usually representing an angle. So we're going to use theta here. And you notice that t is our variable right below it. 18t was 18 degrees per second times the number of seconds that it passed in our Ferris wheel ride. And that was from last time as well. So if we look a little closer at what is happening in this example, we could look at our first quadrant, for instance. So if we had something like about right there, let's say that that is about 50 degrees. So if we basically wanted to get the height, total height, which was basically this x plus that 30 feet right there. So it turns out that we can just take that 50 degrees and just do h, and then we would make this a theta. So we're just going to do h in terms of our angle. So I'm going to do h of 50, and 30 plus 25 sine of 50. And if we grab a calculator, we can figure out what that is going to end up equaling. So in our calculator, we're going to type in 30 plus 25 sine of 50 degrees, and ends up being 49.2. And that is actually the height total, x and 30 included. So h of 50 degrees would be a total of 49.2 feet. And so if you think about last time, with 36 degrees was one of our answers. So 30 plus 25 sine of 36 degrees. The answer we got back then was 44.7, and we don't need to do anything extra. So if we look elsewhere in our circle, we want to see what else we can find using that same formula. So how we're going to do that is, let's say that we wanted to go around that circle a little bit more. So we wanted to go around that circle for, let's say, 130, we'll say 160 degrees, which might be somewhere around there. 160 degrees starting from right here. So normally we would have this whole distance right here, and we would have before had to do 30 plus 25 sine of 180 minus 18t. But we actually don't need to do that. All we need to do is just find h of 160 degrees. So 30 plus 25 sine of 160 degrees. And that ends up being equal to 38.6 feet. And remember, that's off the ground. So we would basically be saying that from that point right there, we could kind of just draw a dotted line all the way down. And we would know that that is 38.6 feet off of the ground. So now if we basically can see that this function, this same sine function, sine equation, gives us for the first and second quadrant the same. So now where things are going to get interesting is if we go into our third and fourth quadrant. So now if I'm going to go around the circle, let's say we wanted to go 250 degrees around the circle. So what we'll say now is that, well, I can actually still use the same equation. So I would be doing h of 250 degrees would equal 30 plus 25 sine of 250 degrees. And that ends up equaling, let's check it out. We have 30 plus 25 sine of 250. That equals 6.51 or 6.5 feet, which if we look at our diagram, 6.5 feet, that looks like about right for that dotted red line area right there. And so if this is less than 30, that would mean that this second part had to be negative. So we basically ended up doing 30 plus 25 times some negative number, and it'd be some negative decimal. Since we ended up with a number smaller than 30, the second part has to be negative. So in the third quadrant, we ended up basically finding a sine value is negative. Obviously, plus 25 has no way to be negative. So the only part that would end up being make sense would for the sine of 250 to end up being a negative number. And finally, let's look at our fourth quadrant. So going all the way around, let's say we went to 300 degrees, which would be somewhere in this general region. So remember, 300 degrees is starting out right here where our ride started in the last two lessons and going all the way around 300 degrees around the circle into our fourth quadrant right here. And so if I take that, so if I'm going to do my height in terms of degrees, 30 plus 25 sine of 300 degrees, that gives me an answer, 30 plus 25 sine of 300. That gives me 8.3 feet approximately. So that's an example again where the sine of 300 ends up being equal to a negative, something negative times 25 added to 30. We know the 25 and the 30 are constants or a coefficient, which are both positive. The only thing that can be negative is sine of 300, which if we did by themselves, so if I did the sine of 250, that's a negative number. The sine of 300, that's a negative number. That is different from one we saw earlier. Sine of 160 is 0.34. It's a positive number. If I did another one from the first quadrant, the one from sine of 50 we started with, also a positive number. So what was ended up being negative was the parts that were kind of lower from the x-axis. So this part was what ended up being the sine part. Remember, we have that being negative for 300 degrees because it's 30 plus 25 times this amount. And then the same thing on the left-hand side. We have this line for kind of from our dot to our middle of our Ferris wheel. That adds a negative value with our 25 for our radius for our red part over here. It was 30 minus this whole red value to this part right here. That was the 25 sine of 250 part. 25 sine of 250. And that's showing that there's basically some places around the circle where you are using sine with that angle, and it ends up being equal to a positive number sometimes and equal to a negative number sometimes. And that is where we're going to pick up in part 2 of this lesson. Now moving into our main part of the lesson in part 2 now, we're still talking about our Ferris wheel, and we talked about our highlighted equation a moment ago. And we're going to now try to think about the angles of rotation for sine around our circle. And our first questions are going to try to understand why, since right triangle trigonometry only defines the sine for acute angles, how we can maybe use it for whole circles. Since it seemed like that is going to be working based on our investigation so far. So now if we are looking at parts 1 and 2, or numbers 1 and 2, Carlos is basically saying that he wants to look into how sine is being programmed into our calculators, how our sine function works in a deeper way. And he says, for some angles, the calculator gives me positive values for the sine of an angle. And for some angles, it gives me negative values. We explored that in finding the heights of different places on our circle using just one equation that I mentioned already, that it's highlighted in front of you. And so in number 1 and number 2, we're going to look for angles of rotation for which the value of sine produced by the calculator should be positive and negative. So let's look at that first. So now, in order to do this, we're going to kind of still think about it in terms of our Ferris wheel. So we're going around in a circle. So we have our circle, and we have the spokes of this Ferris wheel still in play here. And we, on our Ferris wheel, we're still basically working from starting in the same place. So when you have this starting place, that is basically a place where you're always going to be starting here, no matter what the angle you're doing is going to be. Now, I'm going to label initial position here. So we basically have this green line is what is called the initial position. So we're going to be always going from angles from there. So remember what we did in our work earlier in the video, or earlier in general, that we have these sine angles that when you have the ones that kind of the heights above 30, those were adding to 30 for the total height. Same with on the left side up here. And the ones below were negative values taken away from the height of 30. And same thing with on the right side. So we can surmise that the angles that are going to be ending in our first and second quadrants are going to give sine values that are positive, and angles that are going to end in our third and fourth quadrant are going to end up being negative sine values. So to offer some examples, if we had an angle from our standard position in purple here, and remember we're always starting from green right there, going kind of that direction. So let's say that this angle was 55 degrees. If we checked the sine of 55, the sine of 55 is equal to 0.82 approximately. And we could keep checking that. We could go up to an angle of 70 degrees. If I checked the sine of 70 degrees, then we would see that that would equal 0.94. And we could go past 90 degrees. We could go to something like 130 degrees. So if we kind of draw that angle all the way around, the sine of 130 degrees would give us an answer of 0.766, all positive numbers. And then if we look at the bottom part, so if we are going to go all the way around to the bottom, we could go to, say, 190 degrees. These are just approximates. So I would go all the way around counterclockwise that way. And the sine of 190 degrees should give us a negative number of negative 0.17. We could keep going around our circle to say 260 degrees around the circle. The sine of 260 would be equal to negative 0.98. And finally, we could go all the way to the fourth quadrant. We could go all the way around to something like 290 degrees. The sine of 290 degrees would end up equaling negative 0.9394 maybe. So we can see that sine values, if you are in your first or second quadrant, are positive, and sine values in the third and fourth quadrant are negative. And that is something we should definitely have in our notes. So sine of theta is less than 0 if it is between 180 and 360 degrees, as far as we know right now. And then, in addition, the sine of our angle theta is bigger than 0 so far if we are between 0 and 180 degrees. So we might be adjusting as we go on, but as of right now, we can see basically first quadrant between 0 and 180, sine is positive. If it's between 180 and 360, sine is negative. So now if we go back to our notes, our next question here, number 3, is asking about possible angles of rotation where you can't even draw a triangle on our Ferris wheel, but the calculator is still going to give us values for sine at those angles of rotation. So we have to keep thinking about our Ferris wheel in this particular case. So we want to find angles of rotation where you can't draw a reference angle. So if we have our circle drawn again, so for this one, we're going to keep with our Ferris wheel idea a little bit more because we have 25, 25, 25, and 25 for our radius lengths. So we got to keep those in mind. So before, when we were drawing a certain angle, like this blue angle right here, from our initial position to go upwards like that, and we would be able to draw a triangle kind of like that, where we'd have our angle theta there, and the 25 would be our radius, and then this would end up being 25 sine of theta, just like we've done before, and that would give you how long this value is right here, and then you'd add it to the 30 we used before to get your answer. And I could draw one of those little triangles in all three other quadrants. What I can't do is, if I said that I was going 0 degrees around, or if I was doing 90 degrees around, if I was doing 180 degrees around, 270 degrees around, or 360. So we can make that list: 0, 90, 180, 270, and 360. So we're trying to see that basically this 25 sine of theta what it would equal at those angles. So let's try we could try each one of those. So if we did 25 sine of 0, that equals 0, because the sine of 0 equals 0. If we did 25 times the sine of our next angle, 90, we could do 20. Okay, so let's write that. So 25 sine of 90, that equals 25. Because that's just this height. It's always giving us the height above our kind of midpoint of our Ferris wheel, or in other words, our x-axis, basically, if we're thinking about it in terms of a graph. So that would be 25. So that means the sine of 90 is equal to 1. Next would have been 25 sine of 180. If we put that in our calculator, we get 0 again. Well, that's 0 feet above the middle of our Ferris wheel, or above our x-axis, for instance. And we can keep going along this pattern, and you might be able to guess what the next one's going to be. 25 sine of 270 is going, and this one's a little weird, so if we do 25 sine of 270, we get negative 25. Because we're negative 25 feet below the x-axis, in this case, of a Ferris wheel. So if this is 25, that means sine of 270 has to be negative 1. And lastly, we tried 25 sine of 360 degrees. If we put that in our calculator, we would actually get 0 again. And that is, well, if that's 0 in our calculator, 25 times 0 equals 0. That means the sine of 360, just like sine of 180 and 0, they end up being equal to 0. And that is a pretty important development that we're looking at, those kind of ending lines of each of those quadrants. And next, we'll look at number 4. We are now working on number 4. It asks us for pairs of angles that have the same sine value. So a pattern you may have noticed in prior examples was that when you had a place on the Ferris wheel or a place on our circle in front of us that was above the middle of the Ferris wheel or above like the x-axis in a way, well, those ones we're kind of looking at values kind of like going upwards. And then the ones below the x-axis or on the bottom side of the Ferris wheel were going downwards. For instance, if I had 70 degrees right here, the sine value that we would be finding would be the opposite side right there, and that would be positive. And we could figure that out. So we have like a 25 there for our radius and 25 sine of 70 degrees. So if you look on the second quadrant of this circle, and we kind of follow that around, so it turns out if you basically make the same angle with the middle of our Ferris wheel, if we make another 70-degree angle on this side, so that I could draw it like so, starting from our initial position right here in front of us, the angle we want in this part right here is 70 degrees. So like that dotted angle right there. So if I was 70 degrees short of 180, that means that this whole angle would be about 110 degrees, which obviously both of these aren't on the scale, but we're just not going to worry about that right now. So 110 degrees right there. And we can certainly check these answers. If I found the sine of 70 degrees on my calculator, and I found the sine of 110 degrees, if I did this correctly, then that means that the answers I should get would be equal to each other, and they both end up being equal to 0.94. So both of these equal 0.94, 0.94. So if I wanted to know what their height was, well, I know it's going to be 30 plus 25 times those numbers. And that would give me the answers for those I'm looking for. So now if I wanted to kind of think about those two angles, but in the bottom two quadrants instead, I could do that next. So if I want to make kind of that same 70-degree angle with my x-axis, I could kind of keep following this around to kind of the bottom right there. So I would have kind of this dotted red angle right there would also be 70. And that means that 180 plus 70 would make this angle 250 degrees. The sine of 250 degrees, that would be negative 0.94. And then lastly, we could go all the way around to the fourth quadrant. And that would make kind of this dotted angle right there be 70 degrees as well. And that means that we would have 70 degrees short of a full circle, or 360 degrees. So that makes this a 290-degree angle. And remember, we're making like triangles here. Even though they're not like lined up perfectly, they're still all equal based on just our drawing. And though the sine of 290 is going to end up being negative 0.94 as well. So the sine is basically telling us, well, if you make that angle here, even if you go all the way around, the angle you're making is still with the x-axis, how we've been doing it in all these triangles so far. So we have a pair of angles giving us the same, 70 and 110 are the same, and then 250 and 290 are also the same, and they give us the same ones, which is coincidentally, or not coincidentally at all actually, the negative version of the first two. That leads us to number 5 on our classwork. And we're back to our actual notes worksheet here. So number 5 at the very top of our page clearly says right. And if we go around the circle more than once, the calculator still gives us values for the sine of the angle of rotation, and multiple angles have the same value of the sine. And 5 asks us, without using your calculator, list at least 5 sets of multiple angles of rotation where the calculator should produce the same value of the sine. So the easiest way to think about this is if you're on a Ferris wheel, if you are somewhere on the Ferris wheel, if you go all the way around the ride, one full trip, you are back to the same place. So whether you're where you're starting at, you're a certain height off the ground. If you go all the way around the ride to the same place, you're the same height off the ground again, which would mean you're the same sine value of whatever angle you're talking about. So the easiest way to do this is if I know that, say, I was 40 degrees kind of above horizontal. So if you think about like what the circle would look like. So it'd be that, basically that happened. So if I wanted to know a multiple where I would have multiple angles of rotation when the calculator produces the same value, basically you can add a full circle to each of these. So I could add 360 to get to 400, and then add 360 to get to 760, add 360 to get, I'm not sure what that is, 760 plus 360 would be equal to 1120. And the sine of 40, 400, 760, 1120, and continuing onwards would all give us the same sine value because they're the same height on the first wheel. They're all one full circle on the ride apart from each other. And indeed, you could actually go backwards. Like I could subtract 360 from 40, and that would give me negative 320, negative 320 degrees. Remember, this is clockwise now. And that would also give us the same sine value. I could do all 5 of those, would give me the same exact sine value. Number 6, so Carlos says, so how big can the angle of rotation be and still have the same sine value? Or how small? How would you answer Carlos and Clarita's questions? So if it were me answering those, it's actually an easy thing to answer. If you're thinking about a ride in a Ferris wheel, there's no limit to how far that ride could spin clockwise or counterclockwise. So there's no upper limit. It could go to an infinite angle of rotation and still have a sine value. It would just be somewhere negative or positive based on you're going clockwise or counterclockwise. And that's what I'll answer here. So the angle can continue growing or shrinking. Remember, these are basically just positive or negative degrees forever. There is no limit. In fact, you could pick a gigantic angle like 4 million degrees, and you could type that in your calculator, sine of 4 million degrees. Sine of 4 million degrees just equals 0.64, and there is really truly no limit. And the last part of this page, number 7, while you're asking questions, I'm wondering how big or how small the value of the sine can be as the angles of rotation get larger and larger. So that kind of depends on how big your circle is or how big your Ferris wheel is. Because if we know, we'll just draw a little circle here to the left-hand side for number 7. If I know the radius of my circle, so if my radius is 25, that was 90 degrees away from earlier what we talked about. So if you do the sine of 90 degrees, that just equals 1. So in that case, the biggest value would be 25. The smallest value after 270 degrees would be negative 25. And it depends on how big your circle is. So we could say that if your circle or Ferris wheel has a radius of 12, oh no, 25, I don't know where I got 12 from, of 25, then negative 25 and positive 25 are the maximum sine values. Because remember, that's how we figured out where their height was. If we knew they're 30 feet off the ground, we could either subtract 25 or add 25. Sine was giving us the height above the middle of the Ferris wheel or below the Ferris wheel for all these things we've been doing so far. So Claudia's final statement here is, well, whatever the calculator is doing, at least it's consistent with our right triangle definition of sine as the ratio of the length of the opposite side to the length of the hypotenuse for angles of rotation between 0 and 90 degrees. And that's what we found in all of the things we've done with the Ferris wheel so far. We could grab one of our work from number 4 earlier. In our first angle, it was 70 degrees. In here, we used sine to get that far opposite angle. We knew that our radius was 25, and we used that to figure out that, for instance, the 70 degrees, we could figure out 25 times 7 sine of 70 to figure out how high above the middle of the Ferris wheel it was. And next, we're going to look at wrapping up some general notes that we need to remember for this lesson. To wrap things up, we have some notes that we're going to walk through about the value of sine going around a circle. So at the top here, it says Carlos and Claudia decide to ask their math teacher how mathematicians have defined sine for angles of rotation, since the ratio definition no longer holds when the angle isn't part of a right triangle. Here is a summary. So, I mean, that's like sort of true, but we've kind of shown that we're basically able to show that sine can be values anywhere around a circle, given the triangle you're going to set up. So for the first paragraph of notes, so when we have a circle with radius r, whose center is located at the origin on a rectangular coordinate grid, so basically you're drawing a circle at 0, 0 on your regular piece of graph paper. The angle of rotation in standard position, basically what that means is if you look at our picture, so the standard position is, so we have an initial ray here. It's always going to start at that same place. And then we have a terminal ray. And this is basically the angle theta right here that you're going through. And whenever you're going around in a circle a certain amount of degrees, whether it be counterclockwise and positive, so counterclockwise, positive, clockwise, negative, definitely important things for our notes. And whenever you do that, your terminal ray, what I just pointed out earlier, is always going to hit some point x comma y on your circle. And that can happen in any one of your 4 quadrants. So like if I had this same sort of thing where your rays kind of go out in that blue thing there, and you have an angle starting from our initial ray and like that. So if that was drawn, your theta would be the same thing there. And this point would end up being next negative x comma y. You could do the same thing in the 3rd quadrant. You could draw your angle kind of going out there to the left, and we'd have a theta would just be this part in here, and that would be kind of the full angle starting at starting position. And this point would be negative x and negative y in that 4th quadrant. And finally, we would have the same sort of thing happening in our 4th quadrant, where we'd have our terminal ray in the 4th quadrant. We have some angle starting from our initial ray going almost all the way around the circle to get there. And then your angle in here is the same exact theta. And then you would just have the same x here as the original, but just the negative y version of it. And that is going to be important for a lot of things we're going to be doing the rest of the chapter, what we've just went through right there. Something from earlier on is that if I had this terminal ray right here, this is x comma y points, I could start there and go a whole circle around any number of times and end up at the same x comma y points. Or I could go clockwise all around in a negative direction and still end up at that same x comma y point in my 1st quadrant or wherever I happen to be starting. And those are known as coterminal angles. They end together, hence coterminal. And usually you're starting out with some angle theta in both of these, and you're adding some multiple of 360 degrees to yield an infinite amount of coterminal angles if you so choose. And to wrap things up, something very, very important is that depending on the size of your circle, where you have r right here is your radius of the circle, and you can see r in the picture right there. So it turns out that basically if you know sine of whatever angle you have there, it would be the y part right here, and it would be over r. So the sine of any angle on your circle here would be the ratio of your y value of that point divided by r. When we were using a Ferris wheel, it was 25. It could be anywhere from 25 down to decimal points or much larger. But that is going to be a very important point that we will be working with a lot in this chapter, eventually looking at cosine as well and tangent and expanding on this a lot. And that concludes the more sign language lesson. Thank you for watching.